Yeah, so I'm super excited about this next talk from Kristian from Vespa. For those of you who don't know, Vespa got its origin back in the day, the same time as Hadoop, right? Had its time period back in the Yahoo days, and now is its own company. And I'm really excited to have Kristian here. It's his first time at Haystack. And I've looked at Vespa as maybe a pointer to the future, right? It's had sort of features as part of its search engine that most people didn't have, and definitely has sort of pushed the boundary of what is a search engine. I don't know if you're still labeling it a big data engine. Maybe less so now, but the idea of storing content and searching it and serving that content. So really excited to have Vespa here. Kristian, I'll hand it over to you.
Thank you, Eric. That's a great intro. I'll try to remember that myself. I'm Kristian. I'm the only thing in between you and lunch, so I'll try to be brief. So yeah, here's the story. We've been here for a long time. Personally, I've been with the team for 25 years, even before we were acquired into Yahoo together with Alta Vista. So it's a team built of long-timers like me and new people lately. In Yahoo, we worked a lot on search and recommendation use cases. Search cases like mail search that has tens of billions of items. Recommendation cases are more like not so many ads to serve, but you have to serve them really fast. So that was like 100,000 plus servings per second. So the engine was built to scale both in the data and in the query dimensions. Inside Yahoo, we also open sourced. That's soon 8 years ago, or since 2017, Apache 2.0. And we started Vespa Cloud 3 years ago inside Yahoo. We figured out with Yahoo that it was better that we did that on our own. Our business model is very different from Yahoo's. So we spun out 1.5 years ago as a separate company. Some of the users of Vespa are at the bottom. You will see search cases like web search, like the Quant engine. We have a lot of e-commerce cases, both in Europe and in US. A lot of recommendation use cases. My favorite one is Spotify. It's like finding the next best song or the next best podcast. It's like a great example, or maybe even better, OkCupid, finding the love of your life. That's like the best recommendation case I can think of. Recently, most of our cases are for GenAI, and you see Elicit there, it's like for researchers, Ravenpack, BigData.com, and also Perplexity. So we help Perplexity find stuff for GenAI. And that's kind of funny because that takes us back to web search. It's like full circle. Perplexity uses their copy of their web as the R in RAG with Vespa. The funny thing is that it's very different to serve agents than people that we used to do 25 years ago. There was some chatter on the Slack whether about lightning talks. I was thinking maybe we could have a 5-minute on what are the differences we are facing today when we are trying to do web search for the robots. Any interested in doing that? Hands up. Okay. The good news is I have no slides, so there will be a slideless thing. You will be bored of slides after today anyway. So I'll pitch that in Slack for 5 minutes. So we are not going to talk about search. We are going to talk about cars. This is the car of my son. It's a German car from 2004. It's the only thing that holds this car together is the car paint. So Germans are good at making car paint. The car itself will disintegrate. So that is a problem for my son. It's even bigger problem for his mom. It concerned her a lot. By the way, my son is called Magnus. I'm calling M to protect the innocent here. But his mother is called Siri, as an anecdote. So whenever things pop up here, suggestions from Siri, my heart bumps. It's just like, are we redecorating the living room again or something else? Anyway, this is Siri. She is the driving force for fixing this problem of an old car. So I'll use this as an example. So what's important for my wife when she will try to find a car? So she has some criteria. Those are not like hard criteria, but her preferences. It's our son, so the car must be safe. We don't want to repair the car at least too often, so it should be reliable as well. And my wife, she will not see this presentation anyway, but prestige is important to her. So it should be a good brand. Our son can't be seen in a cheap Chinese car. All right. There are some hard criteria as well. It has to be pre-owned, our budget. Even though I'm in the search and recommendation industry, we can't buy a new car or like a brand new car to our son. So it must be affordable. That means pre-owned. Magnus, my son's girlfriend, she's called Ingrid, or I here. She has a driver license only for automatic cars. In Europe, we also have stick shifts. And lots of the used cars are like that, but she can't drive that. So my son is bored of or tired of driving Ingrid around. So it has to be automatic. And the engine size, he's 22, so it can't be like a slow car, low powered. It has to, some engine. So this is one of the bigger sites in the US, I believe, Auto Trader. This is where you go to buy cars, at least one place. So figure you are my wife, and this is what you see. This is the first page you see. And she's concerned about buying a safe, reliable car with a prestigious brand. So, and this is like state of the art in 2025. So there is a problem, if you remember the keynote today. There are problems still. This is not optimal. Because, well, my wife actually does know some things about cars, but will pretend she doesn't. So are these safe cars or not? Are they reliable? Or, how about the prestige? So we need to do some research. So good thing is this site has a research option. Research information. If you click that link, you get this. So the good thing is that to become an expert, it takes only 2 minutes. You have read all the research, and this is everything you can find on the site to research. It's great. But it won't help you find the car, I believe. So there is some potential here. There are still some problems to fix. My wife, she would go here. And this is actually great. She can type, what are safe cars? And Perplexity will tell you. There are 3 brands here. European, Japanese, American. Okay, great. And it also lists the sources, which I love. It's like this happened last year. I think that was GPT-4o and Perplexity and the others. They also included the retrieval and listing how they found it. Same for reliable cars. We have to go to Japan, it seems. Never mind. And we can also find what the internet thinks are the good brands. And then we have to go to the European cars primarily. Anyway, this took me like 3-4 minutes to find out. I know how to map, or she knows how to map her preferences into something that we can use. So safe means these cars, and reliable and prestigious. And this is useful. So one observation I made is that we are all very different. So we think about this differently in how we express, what I like. Maybe my friends, they would like to buy cars that are good for learners. It's like their kids are like 16, they are starting driving. So they just need a car that is super inexpensive and easy to drive. But how do you express that? But you can say, okay, he's getting his license. And there are so many ways you can express this, so you can't kind of pre-define that or pre-calculate it, but we can read what they are typing. So that's why LLMs are great for this. It's like some people would that's their favorite car. How do you search for that? So actually uploading images, I think, will be also a thing. So there are models everywhere. So I'm not going to talk about all of them, but this is like a real system would look like today. You have embedding models that takes your input data and generate embeddings for similarity searches. You have ranking models like gradient boosted decision trees. Those are great for structured data, and you will find them at the index level. So you can train these models to match the user preferences. You have re-ranking models that could be cross-encoders or other more fancy stuff also deployed. And you have large language models that you can host inside your system, or you can host it locally in your data center, or you can actually or just use OpenAI or similar. So this architecture is often found in systems like this. You have the stateless part. In Vespa, these are the container nodes, and the stateful parts, nodes that are those with the index. They scale differently. So the cost is like 90% are on the bottom yellow level here. The blue ones are more like 10%, unless you do heavy embeddings or processing. Okay, so I'll simplify to only talk about LLMs, and as you're just going to use OpenAI API anyway, so it looks like this. So what are the different ways we can use them for? So this is like, remember the classical RAG case where you have a query coming from the user, you send it to the index, get some data, call the context, push that into the large language model, and it kind of synthesizes or summarizes something for you. So it looks like this. So this is like a super way to explore things. You can't click on something or buy something here. I think that will happen very soon. So AutoTrader and the likes really need to figure out something here, because this is like excellent. But it's very different from the way we buy cars today, but it's coming. So this is like the first way to integrate LLMs. The other way is to just use them as re-rankers. You can take results and shuffle them. So in this case, it would look like if this was the result set, we could swap the Hummer with the Mazda using an LLM. You can just ask the LLM, say, okay, here are 10 results for series preferences, rank them. And that works great. And in some cases, you can use this also as just simple classification. You can take the top result, sort them using a search engine, and have like, in some of my experiences, you easily get 90% correct, and then do the LLM re-ranking and get 4 or 5 more. A third way to do this, and for those of you who were at the other theater listening to Yuri, the previous talk, he talked about how can you use a language model to work on your input data, input documents, and expand them. So you can look at the data and you can extract entities. So for those of you planning to create a way to search for cars owned by celebrities, you can easily do that. But there are many other things you can also do. You can, this is very common, to generate questions. What are good questions for this car? This is exactly what Yuri talked about. So we have an example here. So try to spell Hongqi, that's a Chinese car, correctly. I guess no one can do that. But you can have the language model do it for you, and you can also have it create good queries. And then you can match queries to queries, which is super useful, say for search as you type kind of things. You're typing and you're just searching in the queries instead of the data. So you do query suggestions. All right, or you can translate. In Europe, people talk many funny languages, but it's still like a single market. In some cases, you can go to Germany and buy a car. So there are many good cases for using a language model on your input data. But what we're going to talk about today is the queries. How can we use a language model to help my wife find a car, mapping her preferences into something useful? So in this case, it will be like, what's relevance here? This is like, it has no information. I didn't search for anything, and the system doesn't know me. But I can give it some data. So I'm not arguing we should make a chatbot here. It was said there are already enough chatbots, so we're not going to make one. But we are going to allow a user to express what's important for her. All right, so let's see if the demo gods work with us today. So my colleague Radu, he made, some of you know him, made a quick demo. So let's see. So what I just did is I expressed, okay, I would like German cars. And you see here, the system, I'll get into how this works. Mapped this to some German brands. So this is the LLM output in JSON that we are then using to refine our searches. So we'll see, oh, there is a lot of all this. All right, so we changed the preference. So BMW is a bit better for me than Audi, and it changed the results. So with this, we can keep the existing way you're looking for cars. It's like you're searching and you're getting search results here, and you see the facets. But I'm using natural language. So through these preferences, I can kind of fine tune here what's showing up. Yeah, and it says it shouldn't be diesel cars either. So this is a way where we are not like radically changing the way we are buying cars, but we are adding a way to fine tune the results. All right. And the key here is the preferences, is the mapping from what I'm saying to what's sent to the search engine. So how do we do that? But if you take a look, I tried to find someone doing like things like this. I couldn't find one. So, but if someone of you know of this, good services where I can, not a chatbot, but like a way where I can type in my preferences and tune the search results. The closest I found was Amazon's, and this wasn't good. Okay, going back to this. So the problem we are at is that it's like the car is, when you sell a car, there are a lot of attributes of that car that you enter into the system, like the make of the car, what kind model it is, engine size, and all these kind of things. But the problem we are facing here is how we're mapping language into this. So some of this is prompt engineering. I'm not, I haven't done much of that. We are not going to talk much about it, but what we want the language model to do is to output something well-formed, like JSON, that we can use in our queries. And in this case, I want the LLM to give me some JSON. There are recently, like LangChain and others have made APIs that makes this easier. So I think it works quite well. I guess some of you know more of that than I do. But for this case, it's fine. And The good thing is that I'm not asking it to summarize or anything, so it's kind of safe. We don't expect bad things to happen here. So for the query, I prefer safe European cars, I got this output. In my prompt, I also said that I'm not only looking for brands, I'm looking for things like mileage and age. You can select yourself, how much you want from the model. But in this case, it works quite well, I would say. You will have to kind of express some of the relationships between the properties and the language. So how do we do this in practice? It's like the car data. In this case, I just used some Kaggle data, like a comma-separated data that looks like this. But I want to do things like this because as we're going to rank this, we need some more normalized features. So in Vespa, we have something called a mapped tensor. It's like a sparse tensor, where the address of the value is like, like manual can be an address, like manual transmission, price, and those things. So this is what in this case, it looks like a regular map. It's like a mapping from a string to a value. Some of these values are like binary. You are a Ford engine or not. I can see there are cases for a Fordish car, or that relates to Ford. So you could actually build that. But for now, I just say it's a Ford or not. The more complex things is like price. When you're ranking on price, you probably don't want the most expensive car. You want more like a relatively well-priced car. So how do we do that? So in Logstash, you can easily do things like create a function. So if it's like the most expensive car ranks the lowest, things like this, and we'll have to map from input data to data type. So with this, the config is actually as small as this. We can map from the comma separated into these car features here that we will be using for ranking. So keep this simple, because in Vespa you can use the ranking framework to do complex calculations. So when you're inputting data, you want to keep this as simple as possible. So how about the queries? So if you remember the blue things that were modified by my language, we mapped that into features. So this is like JSON-esque, or something that looks like JSON, the way we express a map tensor in the queries in Vespa. So it says that, okay, age is important to me, mileage, and these are the brands that I have expressed. That's my preferences. So the ranking function is super simple in this case. It's just a dot product between my preferences and the car features. So in Vespa, you just express that as a multiplication of the two tensors, and you just sum over it. So it doesn't get any easier than this. So for those of you that haven't done this, most of you have done this on dense tensors, or at least indirectly. So doing a sparse tensor like the map tensor is say, okay, there is a value for all this, so 2 times 1 is 1, and price 3 times 0.7. So and the sum of this is this. So this is the dot product of a sparse tensor in practice. And that's the ranking function. That's how I rank all my preferences. So why don't we see this used more often? So to deploy this to production, well, you have a system today that ranks on something, which is much more complex than this one. But in this example, I say, okay, it could be that you're just ranking on text similarity, so BM25 something. In this case, to add this capability, you just have to add the dot product here. and you're good. You probably also want to add some normalization to this, because as you're adding components, like BM25 is unbounded, so it can easily kind of hide the other feature values. So adding some normalization is important in these cases. So I prefer to keep them between 0 and 1. In reality, the ranking functions are like super complicated. It's like here's my preferences. Where the car is at is important. You don't want to go to Alaska to get your car, or you could, but it should be really inexpensive in that case. Text searches and also model inference. So in Vespa you can do model inference as well on your train model. That's on the yellow nodes, if you remember that. I also simplify this a lot because you also want to do multi-phase ranking. Some of the rank features are expensive to calculate, so you want to do that on the top K. Here I just put this in the first phase for simplicity. Okay, so I think why don't we see this? It's not like a technical problem from the search perspective. It's not much more than we just saw to implement this using the preference tensor, at least in Vespa. So that's probably not the blocker why we don't see this. So we are trying to add a feature to express preferences in natural language. Very few services does this today. But GPT and Perplexity and the others are targeting that, but from a different starting point. And I think those will meet somewhere. And if the car dealers don't do something, they won't be there for long. Just because it's very powerful to, at least someone like me that doesn't know much about cars, to let the system help me. It's like the analogy is like if I want to buy a TV and go into a TV shop, a physical one, if you remember those. And I enter the store and say, I want to buy a TV, and they say, well, what kind? I don't know. Oh, you haven't done your research. No. Okay, so you go to the library down the street and do that research and come back. That's the analogy of what that car site did to me, because it didn't help me. I think it's important to, if you're doing this, to display the preferences. So why do I see the cars ranked like this? Why are there so many Audis? I didn't mean that. I want some other options too. So some way to see that and tune it. We don't see much of that either. Maybe it's just too hard to build. Maybe you don't want this preference crap at all. So there must be a way to disable it. There is also the problem, it's like in this demo, the language model answered me back and we saw the text, and that's kind of scary because people type all kind of things, and people owning the brand of the site you're at, they don't want that really. So you could actually opt not to do that. You could just have the user type and update the preferences like we saw. That could be like a softer way to get started with this. And how do we actually educate the users to do this? So I think some way of doing some canned queries or some examples or something. Okay, so you can just type here. Okay, so you have a 16-year-old. Okay, so you need some car that he can crash when he's when he's getting his license. So I think the challenge for us is more on this side than on the ranking side. The ranking side is easier. So I'll talk a little bit more about tensor ranking. Tensors are important to us in Vespa. We added them 10 years ago. Tensor is a more generic data type than a vector. A vector is like a one rank tensor. You're all very used to these kind of dense tensors like this. We spent many years in Yahoo doing things like this. You have a lot of source data. You use a machine learning model to generate a tensor. So nobody has any idea what goes on in position 4 in a tensor. It's only the model that knows this. So we can't parse that. But these are the vectors that people are using in vector search, and you're looking for vector distance. The map tensors are the same, but the dimensions are defined by us, which makes it usable because we can understand it and change it. But the way we use both the sparse and the dense tensors are, it's the same. We are just calculating the distance. So you can actually play with this. Maybe we'll try a live thing again. It worked the first time, so maybe now too. So we have this, what we call the tensor playground. It lets you experiment doing these things. So we can say, oh, I'm much more price sensitive. Yeah, and it will recalculate. So this is a great way to getting into using tensors in your ranking. And I think you should, because there are so many interesting problems you can solve with this. You can actually implement a neural network using tensors. And there is an example here. Other things I can think of that our users have used is like self-driving cars. They have so many sensors, like 20 cameras or something. How do you use that data stream to something useful? But some used it for finding out, okay, for this stream of camera data, and you have 20 cameras, so the tensor keeping this needs a dimension for the camera name. And you are looking for similarities in your vast test data set. Okay, have we covered the use case of an 8-year-old driving over a cat on a red light? Do we have that test case? That's the problem. But you can use similarity searches to do that. But if you have like 20 cameras, it is a lot. But it's all formulated in tensor mathematics. Okay. Yeah, I'll skip this. There are some links. There is a QR code at the end there to get to this stuff. So the summary is we want to add capabilities for our users to use language, but we don't want to change our site completely. We don't want to build the next Perplexity. We want to keep the car site, but we want this capability. It's very easy to transform your data to make it rankable using the map tensor with the rank features. We use a simple dot product. You can go crazy on this, on making any whatever fancy ranking function you want in Vespa. It's just like mathematics. It operates on tensors and scalars. And you add this in your hybrid ranking profile. And by that, I mean, you already have some ranking. With this, you can just create a new rank profile, experiment with this, do A/B testing. Yuri talked about this in his talk. And you'll see if it makes it any better. For you that wondered, this is the car we found and bought. Norway is close to Sweden, so it had to be a Swedish car. And it's great. The fun thing is that actually we had to drive like 8 hours to get it, so our sensitivity to location was low. So those are the things that we could actually use by this and say, okay, I'm willing to drive for a day to get the car. So now we have some closure, what car we got. All right, I think that's it. I'm here. It's my first time at Haystack, so I really enjoy this. I hope we'll get a lightning talk. There are so many things I just omitted now that we can talk about, all the cool stuff that is going on. And I'm here until Friday, so thank you so much.
All right, we have a few minutes. You have put your lightning talk in on the thread on Slack, right?
Well, I will. If there were 0 hands, yeah.
Right, there is. Oh, thank you for bringing up. Do we have some questions? We have a couple minutes for some questions. Do you want to just hand? And then just hand it on to the next person so I don't have to run around.
Can you hear me?
Yep.
So this made sense for cars which have external customer-facing attributes, which are color, brand, and whatnot. And then a car also has tons of internal attributes which you do not expose to the customer. So now let's take this and move the context to an industrial supply distributor who has to sell a lot of manufacturing parts, has a lot of attributes, and the customers are essentially the provider or distributor is searching over attributes that are 100 attributes per product, right?
Yep.
So can you talk a little bit about how does this scale? I haven't fully absorbed the math yet. Does this scale for a large number of attributes? And the second part of the question is, even if I had like a language model translate the way in which they express preferences to my under the hood attribute set, and how does that scale essentially?
Okay, so let's do number one first. So there is a reason why NVIDIA is so successful. It's like the computers love this tensor math because it's very parallelizable, and doing a dot product is super cheap. And the talk before this one was also on binarization. So there is a lot of work going on to make this faster and use less memory bandwidth. So the answer is yes. In this case, it's like 100 dimensions is nothing. It's like normally you see like 384 or up to 3K dimensions or size of the vector. If you binarize it and do a Hamming distance, it's like just a few CPU cycles. And you use a multi-phase ranking function, so you can re-rank the top K using more advanced ranking. So that, of course, the problem you will see is mostly memory that you can address with binarization or doing like bfloat 16 or int 8 or even int 4. So that's already there. Your second question, I think you need to say again because I already forgot it. Yeah.
The question is, I think you defined in the prompt a set of attributes to map onto.
Yep.
Right? That operation becomes harder if you have 100, 200, 300 attributes of the product.
Yes.
And I have to now go from general attribute speak to technical attribute speak.
Yep.
And that has to happen in somewhat real time.
Yes.
How do you think about that?
Yeah, so the context window sizes have grown a lot. It's like now there are 10 million plus. So that's the latest, I think. So you can stuff a lot into your prompt without it being too slow. But yes, it's a concern. You can easily test this also with your, running your models locally, or you just pay for it with the providers. So one thing is the runtime. The other thing is the complexity. Is like how big will your prompt be, or will it be like a library of different prompts for the different things? So I think it's a very valid concern. So I think if I was this company, I would start easy and think what are most people's most concerned with, like brand, mileage, those kind of things, and just add. It's very easy to do bucket testing to see changes in latency. But that's a great question.
Really nice work. I love it. I hope that this approach using LLMs will popularize the sort of soft criteria search, which has been technically possible forever, but it's too difficult to implement, I think, for most people. But this brings up a problem, which is when you have these criteria, you can over-constrain, you can under-constrain. If you over-constrain, the answer is typically 0 results. I want an f2 lens that goes from 10 millimeters to 1,000 millimeters. So sorry, there aren't any like that.
Yep.
Well, in that case, you probably want to say, let me educate you about lenses rather than anything else. And I've tuned these things by hand before machine learning. Well, I didn't have the data for company search, let's say, which is the most important company that matches, whatever, doesn't matter. So I tune it by hand. Some characteristics were logarithmic, some were multiplicative, et cetera, all done with my very fancy machine learning technique. And it worked very well. So in this case, you're delegating a lot of responsibility to the LLM for the weighting strategy, let's say.
Yep.
And if you have an over-constrained case, you say, well, I can give you a 50 millimeter lens that has f2 for only $200, or I can give you a 50 millimeter lens that's 1.2 for $2,000. Which one do you want? It's a huge space of possibilities. If you're delegating all of this judgment to the LLM, you've lost control in some way. How do you deal with that?
Yeah, so that's super interesting. So of course, the output of the LLM that you specify to be a JSON, you can add some code working on that. It's like in Vespa, you can plug in your own processor. So you can kind of, either you can constrain it and say, okay, hey, you're totally out of bounds here. Or you can say, well, this combination we'll just exclude, or you can...
Right, but then we're back to the manual tuning part, which people were unable to do in the past and which LLMs enable.
True. So in my case, I said that, okay, my values should be between -5 and 5. So you can tell the LLM and say, okay, you're only allowed to output data within these bounds. So you can do that. You want to do most of those things in the ranking function also that you can do. You can define functions in the rank profile, and you should do. Why I'm saying this, we see many teams, because they want to implement this like very fancy way of filtering and ranking, and they create plugins. And that's great, because George is good at that. Problem is when he leaves the company. So what to do? So we want people to express their problem in the tensor mathematics, because it's there. So it's easier to manage, and it's more general, and it's easier for us to write software that performs well on a more generic problem. But we should talk more about this, because it's a very good problem.
All right, got one more question. Think we got time for one more.
Thanks, good talk. When we've experimented with this, we have one of the opportunities and the challenges is attribute intersection, where you want a set of features and you have a level of preferences associated with those, but one of your musts is the deal breaker. And being able to evaluate intelligently, well, we don't have that with this feature, but if you give up this feature, you can have more of what you've got, some of your other criteria. And the interplay between those musts and those preferences has been difficult to navigate. Do you have any comment or thought on that?
Yeah, yes, that's a common problem to have. Many times teams write tiered ranking functions. That's so you can kind of implement a filter in ranking. And you can, because you have access to all the attribute values anyway, so you can have if statements and say, okay, so if this attribute has this value, disregard this one. Or if it's like this, multiply by 10, or do something else. So you can express that in your rank profile. And again, you should, because it's done very transparent how these relations are made. So yeah, so tiered ranking functions is a way to solve that.
Terrific. All right. Well, thank you very much, everybody.
Thank you.
Thank you, Kristian.